Welcome to classwork 10.2. This is our final day of calculus prep. So let's take a look at the first example here. Piecewise functions and continuity. If f of x equals x squared minus 1 over absolute value x minus 1, write this as a piecewise function. Okay, so highlight this, piecewise function. Hopefully we remember what that means. If you forgot, take a look at this. This is an example of a piecewise function here. Piecewise. So to do this, I'm going to give you a couple tips here. Up here, we're going to write breaking up an absolute value. So if I have absolute value of a box like that, we can think of this as two separate situations. If the box is positive, meaning bigger than 0, nothing happens. It's just a box. If the box is less than 0, then negate the box. And look at that. That's a piecewise function. So if you're not sure what that means, really think about it. Imagine this were the number 2. If it's the number 2, the absolute value is just 2, and look, it's 2. Nothing happens. However, if this were negative 2, that means the box is negative, so this goes right here, and that's how we make the absolute value of negative 2 into positive 2, because look at that, negative 2 becomes positive 2. So that's how we're going to use this idea. So let's write it out here. Let's first write it as a piecewise function. So I'll write f of x is equal to big bracket. This is a little more complex, so look at the top here. Let's factor that. X squared minus 1, that's x plus 1, x minus 1. But now there's an absolute value, and it's x minus 1, so that's our box. So in order for the box to be positive, that would mean our condition is if x is bigger than 1. So if x is bigger than 1, like let's say it's 5, the absolute value does nothing. You just write x minus 1. Easy, right? The second one, the other condition would be, well, what if x was less than 1? So let's write that there, x plus 1, x minus 1. If the box were negative, that means you have to negate the box. That's negative x minus 1. There we go. Now notice how we can reduce it. So let's go one more step. The tops, these will cancel. So the function is x plus 1 if x is bigger than 1. And then bottoms cross out there. And it's negative x plus 1 if x is less than 1. So right there is our actual function we want to work with. So I'll put a box around that. Now let's answer the question. A, find the limit of f of x as x approaches 1 from the left. So 1 from the left means we want to think about this one, if x is less than 1. So plug in 1 right there, and you're going to get negative 2. B, the limit of f of x as x approaches 1 from the right. So that means 1 from the right means what if x is bigger than 1? So plug in 1 right there. You get 2. And part C, limit from both directions. Well, notice how these two numbers do not match. So the limit does not exist. First example done. Next example. Given the function, and I already noted that's a piecewise function, find the value of k so that f will be continuous at x equals 3. So how did this word continuous? We talked about it a bit in class. In calculus, you'll get the formal definition. I'll give you the informal definition here. So an example of a continuous function would be something like this, like a typical polynomial function, like that. Think of a function that has no gaps, holes, or like vertical asymptotes, or you can draw it without lifting your pen. Again, that's the informal definition of how to understand continuous. Okay, so that's going to be continuous functions. Again, in calculus, you'll get the formal definition. So here it says, given this function, complex, pretty interesting there, find the value of k so that f will be continuous at x equals 3. So essentially, we're trying to figure out how do we make these functions match. So if you imagine this, I'll do a sketch. This is not accurate of what it would be, but the concept would be, here's some function. There's going to be a hole, because this thing is not defined at 3. So let's say this is 3. We want to fill that hole right here. So we want this to be k. So that's what we're trying to figure out. Now, the way we're going to do that is use a limit. What we need to figure out is the limit of this top thing right here. We want the limit as x approaches 3, this number right here. And I'm going to call this blue box because it's kind of big to write. We want the limit of the blue box as x approaches 3 to be k. So this, again, is our goal as we're thinking and working. So let's try it. I'm going to grab that blue box right there, and let's work with it algebraically. So I want to find the limit as x approaches 3 of that entire thing. The root of 5x plus 1 minus the root of x squared plus x plus 4 over x minus 3. So notice how we can't just plug in 3. If you try it, you're going to get 0 over 0. That's indeterminate. And now we know we have to simplify it. We see a bunch of radicals, so that means we definitely got to use the conjugate method. So let's multiply it by the conjugate. The root of 5x plus 1 plus the root of x squared plus x plus 4, all over the same thing. Okay, so let's go down. Limit as x approaches 3. The top works out pretty nicely. 5x plus 1 minus the quantity, x squared plus x plus 4. The bottom is a bit messy, so we don't want to simplify that. Let's just write that as x minus 3 multiplied by the root of 5x plus 1 plus the root of x squared plus x plus 4. But now notice that top we can simplify, so that's going to be negative x squared minus x minus 4. And then that's going to simplify even further. That would be negative x squared plus 4x minus 3. And now the bottom, that's x minus 3, root of 5x plus 1 plus root x squared plus x plus 4. Hopefully you notice that top part is factorable. So I'm going to factor that negative out right there. So that's plus. Let's make that a minus. And now, hopefully you see it. That actually factors to x minus 3, x minus 1. So I'm going to erase this here. And look at that. The x minus 3's cancel. And now I can plug in 3. So if I plug in 3, I'm going to get negative 2 on the top. And then that's going to be root 16 plus root 16. And that works out pretty nicely. That's negative 2 over 8, which is negative 1/4. So there's your limit. And now, take a look at our goal right here. That's it. So I'll write the answer. If k equals negative 1/4, f of x will be continuous. And there's our answer. Okay, second example done. So now let's do the final part of the lesson. We're going to do trig inequalities. So all the skills we've been doing in trig are going to lead to this and your ability to do this fluently. Remember, our goal for inequalities is you always want the piece here to be greater than or equal to or less than or equal to 0. That's always your goal. So make sure you highlight this part right here. That's always what we're trying to do. So here, we'll manipulate it. 2 sine x minus 1 less than or equal to 0. And now I figure out what makes it 0. So that would be when sine is equal to a half. And now I'm going to write my zeros here. Would be pi over 6 and 5 pi over 6. Now inequalities, it's going to be a little different. Our interval, notice at the beginning of the problem said 0 to 2 pi, and that's going to be true for most problems you're going to do. So 0 is here, and 2 pi is here. So we're not going to work on the interval we normally work with, which is all numbers. We're only going 0 to 2 pi, which is the full circle. And we're going to mark our zeros on this. So pi over 6 will be somewhere right here. And to make it equally spaced, I'll just put 5 pi over 6 over there. And we got to figure out where this is positive or negative. Now, luckily, the piece we have is just 2 sine x minus 1. So 2 sine x minus 1, I'll put that over there. And all we got to do is plug in numbers to figure out is it positive or negative. So for example, if you're trying to figure out, let's say this interval right here, an easy number to plug in would be like pi. So plug in pi to that piece, you get 0 minus 1, that would be negative. If you're trying to plug in something here, an easy piece or easy number would be like pi over 2. Plug in pi over 2, sine of pi over 2 is 1, so 2 times 1 is 2 minus 1, that's positive, so let's write positive there. And this last one, this region, notice how you got to pick something between 0 pi over 6, and it's kind of hard to actually work it out, so it's better to kind of think of it conceptually. If you were to plug in pi over 6, you get 0, and if you go above that, it's positive, which means this part should be smaller, so that part has to be negative. And now we're going to circle our answers here and here, because that's a negative answers, and we write it out. Inclusive 0, because that's our interval, to pi over 6, union 5 pi over 6, to 2 pi. And 2 pi we do not include because that's redundant with the 0. And there's our answer. Next one. Now we're going to be using some identities. So you have to know sine 2x. That's just 2 sine x cosine x. And let's move the cosine x over. So that's cosine x. And then you have a 0 now. We're going to factor. So cosine x, and then 2 sine x minus 1. And then from here, I need you to be able to do this part in your head. The zeros. So think, what makes cosine 0? That'd be pi over 2, 3 pi over 2. And the inside part, you're looking where sine is a half. So that would be pi over 6 and 5 pi over 6. Now we make our number line. Maybe make it a little bigger. So 0, 2 pi, and now we have to put in order. So the smallest one is definitely pi over 6, and then it goes to pi over 2, 5 pi over 6, and then of course 3 pi over 2. So notice how there's quite a few intervals here. So now we're going to write down the expressions. So again, make sure you understand that these are the two expressions you're working with. Cosine x, 2 sine x minus 1. And let's start plugging some numbers in. So I would do the cosine part first. I think this looks pretty easy because cosine is just like the x-coordinate. So think about your circle. In quadrant 1, you're positive. So these are all positive here. That's quadrant 1. And once you go to quadrant 2, you're negative. And in quadrant 4, you're positive. So that's not too hard. Now the 2 sine x minus 1, that's again a little bit tricky, but luckily we did that earlier, so we kind of talked through that. So 0 to pi over 6, we said earlier that was negative. Pi over 6 to pi over 2, that would be positive, and that should mirror to the pi over 6, or 5 pi over 6. And then from here, notice how once we dip below 5 pi over 6, we're going to quadrant 3. And in quadrant 3, sine is negative. So these last ones should all be negative, because in quadrant 3 and 4, sine is negative. Now here's our therefore. Remember, this is the answer row. Now multiply it. Negative, positive, negative, positive, negative. And we circle the ones that are positive, because that's what we want. And there's our answer. Pi over 6 to pi over 2, union 5 pi over 6 to 3 pi over 2. Now, some of you might remember that trick we worked on earlier this year where the signs alternate. In trigonometry, that does not work because of the circle. So while it's looking like it does work here, if you do that on all the problems in the homework, you're going to get stuff wrong. So remember, do not do the alternating trick. That does not work in trigonometry. So now let's go to our last example. Sine squared x is less than 3/4. And if you move that over, it looks like that. And you might be thinking, how do you do that? Now remember, this is a difference of two squares. Even though it might not look like that, this is a factorable equation. So let's write sine x minus root 3 over 2, sine x plus root 3 over 2. And look, we got it now. The zeros where sine is plus or minus root 3 over 2, that's pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Let's make our number line 0 to 2 pi. Let's put them in order. Pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. And again, you have to understand you're writing these pieces down. Sine x minus root 3 over 2, sine x plus root 3 over 2. And some of you might just do that part in your head. That's perfectly fine as well. So let's work with the first one. So if I plug in a number between 0 and pi over 3, let's say pi over 6, that's a good one. So sine of pi over 6 is a half. So half plus root 3 over 2, that's definitely positive. Half minus root 3 over 2, negative. Now once we're in pi over 3 to 2 pi over 3, we can pick a number like pi over 2. And sine pi over 2 is 1, so definitely these are both positive. For this interval, let's pick pi. Sine of pi is 0, so that's negative, positive. For this interval, let's pick 3 pi over 2, because that'd be negative 1. So those are both negative. And then for this interval, let's pick 11 pi over 6, because that'd be negative half. So this one should be negative, and this is positive. And there we go. Negative, positive, negative, positive, negative. We want the negative answers. And we got it. There it is. 0 to pi over 3, union 2 pi over 3 to 4 pi over 3, union 5 pi over 3 to 2 pi. And remember, just because they alternate in our examples, that does not mean it works every single time. It will work once in a while, but again, in trigonometry, because of the circle, that is not a pattern, that's not a valid method you can use.